Always wonderful to have Zohreh here. She's one of the leading experts, I think, on simulation of quantum field theories on quantum computers. And I'm really excited to hear what you have to say. Take it away.
All right. Thank you very much. I'm trying to figure out how to proceed with the slides. Is this the right remote? Doesn't work? Yes, I suppose. All right, I'll get us started, but I need help to proceed with my slides. Thanks very much for this opportunity. It's a great pleasure to be in this very nice conference and be able to tell you a bit about, okay, I still want my first slide. Ken, were you able to proceed with your slides yourself? Is this the right remote? This one, okay. Perfect, so that solves one big problem. All right, so I'm going to tell you a bit more about this program on quantum simulation for nuclear and particle physics. How do we go about simulating nature's fundamental particles and interactions? So let's set this stage and see what kind of problems we are after and what is our eventual goal for those of you who are not necessarily thinking about problems in nuclear and particle physics. So we have an overarching goal. We would like to do simulations from first principles. And for us in nuclear and particle physics, first principle means a standard model of particle physics. This is a set of quantum field theories describing fundamental interactions in nature in the form of a strong force, weak force, and electromagnetism. And associated with these forces, there are a number of gauge bosons. And of course, we have matter, and that's mostly leptons and quarks in nature. And all of these particles and interactions nicely come together in this framework of a standard model. Because of many decades of experimental and theory work, we know that this is the verified fundamental theory of nature, at least for these three fundamental forces that I mentioned. However, being able to perform first principle simulations and computations is starting from these degrees of freedom and learning something about the physics of many body phenomena in nature in the form of dynamics and phase of matter is going to be really challenging. Okay, so what kind of problems we're after? We would like to understand the nature of supernovae and origin of heavy elements, for example. We would like to understand possibly exotic phases of strongly interacting matter. For example, those kind of matter that occur in the interior of neutron stars, which are the densest form of matter in the universe. We would like to understand whether a standard model is complete, or of course, we know that it is potentially not complete. We would like to see whether some of the fundamental symmetries that are respected in the standard model are violated, even if by a tiny amount, so that we can learn something about the physics of the beyond the standard model. And sometimes in order to do that and recover and uncover those hidden symmetries and interactions, we use ordinary matter, atomic nuclei, to be able to learn about these tiny effects of new physics. One of those new physics is dark matter, of course. So we are searching for dark matter candidates, sometimes through experiments that rely on the interaction of these dark matter candidates with ordinary matter. And some of the more intellectually interesting questions, like how finely tuned our universe is, if I change the values of the fundamental parameters of the standard model, for example, what is the strength of the quark-quark interactions and gluonic interactions, would that completely change nuclear physics? Would we still get a carbon and oxygen-based life on Earth? Okay? So these kind of fundamental questions, we really need to go all the way to the standard model and have a bottom-up approach to these kind of problems. So let's just set the stage and kind of give a background of where we stand with this problem. Obviously, we are not going to solve everything with quantum computers yet, and we haven't been just sitting back and waiting for these quantum computers. There's been quite a lot of technology developed to address some of these problems using classical computers. And I always like to show this slide, which is a snapshot of some of the early papers that started this field of simulating fundamental forces of nature in form of lattice gauge theories. This is a paper that came out of Columbia University group about 40 years ago. At that time, they had access to classical computers that were at least 10 orders of magnitude slower than what we have today. And they were only working with a few kilobytes of memory. So as a result, the computations that they started were pretty small. So this is a result of a Euclidean space-time lattice that is only 4 sites in extent. So that might remind you of some of the computations that we do today using quantum computers. Okay, so the field of classical simulations 40 years ago was about at the same point that we are today with quantum simulations. Another important factor is that at the time that this classical hardware was being developed, these lattice gauge theories did not sit alone and just think about their theory problems. They worked pretty hard with hardware developers to be able to understand how to come up with the best strategies and networks of these processing units to be able to do this particular task of simulating, in this case, SUN gauge theories, which are a bunch of matrix manipulations and multiplications and so on. And what is interesting is that they actually worked with the IBM hardware developers, and this effort of lattice gauge theories working with IBM led to the development of the Blue Gene series of supercomputers. They've been very successful in high-performance computing over the decades. So this is something to, again, keep in mind as we enter quantum simulation era. For these problems, applications are important, and sometimes they impact the development of the hardware. So let's just move forward by 40 years. Today, we have access to some of the largest supercomputers out there, like this Frontier machine at Oak Ridge National Lab. And because of all these remarkable theory, algorithm, and co-design efforts over the decades, now we can run for each of these computations of the order of hundreds of millions of CPU hours or comparable GPU hours, and be able to really access the physics of the standard model at a very fundamental level. So there are many, many success stories that one can tell about this program. In fact, this program has been supporting a multi-billion-dollar experimental effort in nuclear and particle physics, all the way from exploring the nature of neutrinos and dark matter to understanding and discovering violations of fundamental symmetries in nature, all the way from CP violations to violations of, for example, lepton number in the standard model, as well as understanding the structure and reactions of hadrons and nuclei in these experiments. So this theory program is very important. It's starting to really supplement all these experimental efforts, okay? Let me just be selfish and give you 2 examples of the results that you can already get from these classical supercomputers. And I'm showing these results because they're kind of dynamics. So it is not true that we cannot do dynamical problems with classical methods. We can't do everything, every dynamical problem, obviously, but there are certain kind of dynamical problems that we can do using these classical supercomputers. Each of these calculations, again, are hundreds of millions of CPU hours computing time, and they take years, essentially, to put together. One of them is the first calculation of a proton-proton fusion cross-section that is rooted in the standard model. So you start from quark and gluon degrees of freedom, and are able to predict the rate of the reaction process for this very primary process in energy production in stars like sun. Okay? Another process that is quite interesting is this exotic process, which is called neutrinoless double beta decay. This is a process that would not occur in a standard model, but there are, again, billion-dollar experiments that are running or planned to be able to discover a process like this that would tell us that a standard model is broken. And it is very important that we understand the rate of this reaction from first principles. It is true that there are some non-standard model effects in this process, but there are a lot of standard model effects in this process as well. And it is our classical supercomputers that allow us to, for the first time, compute the rate of a reaction for an exotic process like this that is rooted in the standard model. Okay? So we have gone a long way to be able to enable these first principle computations for nuclear and particle physics. But of course, this is not the end of the story. The examples that I just showed you were in the realm of few-body physics. We have to be careful when I say few-body physics, the computations are still essentially infinite-body physics, because we have all these quarks and gluons, which are relativistic objects, and we're dealing with quantum field theory. So these are very large computations. So at heart, they're actually many-body calculations. But in terms of kind of the physics that we're interested in, we're interested still in properties of large atomic nuclei, in properties of the interior of neutron stars and supernovae. So these are macroscopically larger objects that we would like to describe from the standard model. So that's even a different level of complexity, right? So the way that the community has been approaching this, in the absence of quantum computers, right, with everything that we have at our disposal at the moment, is that we start from the standard model. We predict a few observables in the few-body sector, like proton-proton fusion rate, like neutrino star beta decay rate. But at some point, we hand over this input to the people that are building effective field theories of these problems, in which your degrees of freedom are not those of the standard model. They're not quarks and gluons, but rather effective non-relativistic particles like neutrons and protons and all sorts of hadrons. So then based on that input, you can find out what is that residual strong interactions between these effective degrees of freedom, protons and neutrons. So then essentially you have a non-relativistic quantum many-body problem to solve, as long as you have these nuclear Hamiltonians. So then you go ahead and use your favorite many-body method to be able to solve this problem. Of course, even at that level, this is a computationally hard problem, because even non-relativistic quantum systems are hard to simulate, as we well know, for example, in quantum chemistry, right? So that's sort of the path, and that's how the community is proceeding at the moment. But that, unfortunately, doesn't mean that we are all set. There are still a bunch of problems that we need to solve. And possibly our classical computers cannot allow us to do that. Why is that? So why can't I just apply these successful classical methods that I just mentioned to calculate the properties of a large atomic nuclei? Say germanium. It's a very favorite isotope for a bunch of experiments that are trying to detect dark matter or neutrino star beta decay. Can we just compute this object from first principle? There are a few exponentially hard problems on the way to do that. First of all, the complexity of these systems, these computations, grows factorially as a function of the number of the quarks that are in these objects, right? So if you remember from your elementary particle physics course, if you have taken it, in a nucleon, a proton or a neutron is a combination of 3 quarks, although that's a very naive picture. It's a lot more than that. But even in that naive picture, as a number of the number of nucleons in your system grows, then you have even more quarks, and you have to think about this factorial growth, which is pretty bad. There's also severe signal-to-noise degradation problem. We do calculations in Euclidean time in order to make Monte Carlo sampling methods feasible. And because of that, we run into something that is very similar to a sign problem. It's called signal-to-noise problem. As a function of Euclidean time, the signal exponentially decays compared to the noise. It's very hard to then extract ground state properties and low energy properties of these systems. Another problem is the fact that excitation gaps in these larger atomic nuclei are pretty small compared to sort of the typical energy scales in these systems. For example, we're talking about many orders of magnitude difference in the first excitation gap compared to the ground state energy. How are we supposed to resolve these excitation gaps if we have to deal with that exponential signal-to-noise ratio problem as well at the same time? So that's why we've been quite limited in applying these classical Monte Carlo sampling methods to these kind of problems, except for few body systems, a few nucleons, okay, light atomic nuclei. Those are the kind of things that are possible. So if we make this problem even bigger, as I said, we want to look at the interior of neutron star and understand the phases of matter as a function of density and temperature, then we run into even harder problems. We have the sign problem now that is facing us. So understanding those exotic phases of matter, transitions, critical points that are very important for us, and one of the holy grail problems in our field would be very difficult. Again, there are really large scale experiments going on to be able to probe aspects of these phase diagrams. Not everywhere in this phase diagram is accessible at the moment. But unfortunately, we don't have a lot of first principle theoretical tools to be able to understand what's going on. Now, think about these phases also in real time, because we know that these phases are going to occur as a function of time, for example, in early universe, or after the collision of high energy particles in our colliders. But how we can probe these phases as a function of real time is a pretty difficult question again. And so we would like to have access to these real-time properties of matter, which are the kind of problems that we cannot, again, access with our classical Monte Carlo because of the sign problem. And there are other problems, including the role of neutrinos in the dynamics of dense astrophysical environments. And again, these are highly correlated, quantumly correlated quantum mechanical systems that are beyond the reach of our classical methods. And therefore, our predictions for the role of these objects in the dynamics in these environments is pretty limited at the moment. So these are the kind of problems that would form the basis of the next revolution in terms of simulation and computations for us in this field, okay? So that's why we think that quantum technology can give us that way forward, okay? So the way to think about it is, obviously, we're not gonna stop doing what we've been doing for many decades, but along the way, we would like to also explore this path of performing these first principle simulations, starting from the standard model, using quantum methods, and get to the dynamic and phases of matter down here. Another very promising path is to also try to apply quantum methods to the problem of many-body nuclear structure and reactions. So not only starting from top there, which appears to be more complicated because those are relativistic systems, but also starting from down here when we are dealing with non-relativistic but quantum mechanical systems. So these are problems that are closer to quantum chemistry. But we're going to explore both paths, okay? So how do we then proceed? Maybe one way to think about these problems is to compare them with something that people are more familiar with. For example, simulations in quantum chemistry and material science. So let's talk about the first path. When you go all the way from the standard model, these relativistic quantum field theories of nature, down to properties of matter. So starting from the standard model, we're dealing with both bosonic and fermionic degrees of freedom. These are dynamical, they're coupled. Not only they exhibit certain local symmetries, you also have these important local or gauge symmetries that you have to retain. These systems are relativistic, as I emphasized before, and therefore particle number is not conserved, and the vacuum state of the theory can be quite non-trivial in strongly interacting quantum field theories. Another important point is that for us, continuum limit is very important. So we're not just looking at these lattice problems, but rather we're interested in understanding the physics of the continuum limit, so we better develop algorithms that scale well in that limit as well. So what about this second path that starts from nuclear Hamiltonians, these effective degrees of freedom that are neutrons and protons? So as I said, these are more similar to quantum chemistry problems, but still they are different, okay? So in what way? We have increasingly complex Hamiltonians that are sometimes even unknown with arbitrary accuracy as we go to higher body systems, okay? There are short, intermediate, and long-range interactions. There are 3 and multi-body interactions. And nucleons, protons, and neutrons are not sometimes the only degrees of freedom. We have to worry about pions and all sorts of hadrons in nuclear physics that can become dynamically important as well. Okay? So these are the features, and I come back to these two pictures when I give you some estimates of the quantum computational cost of doing dynamics in each of these pictures. Okay? All right, so how do we start? What are the questions to address, and what do we need to develop for this program? So as with many other disciplines, this is a new technology, and in order to take advantage of it, we turn out to have to do a lot of theory developments, a lot of algorithmic developments that are coming with more novel algorithms or trying to leverage what is out there and apply it to these problems. But along the way, we have to do a lot of implementation and benchmark on the existing hardware. And as I mentioned, maybe engage in a co-design program, just as it was the case in the early days of lattice gauge theory programs with classical computers. We may have to still push on that co-design frontier to our benefit. Okay? So let me give you a few examples of what kind of questions we have to worry about when it comes to theory developments. So the starting point for quantum simulation is a Hamiltonian, right? So the Hamiltonian was written down many decades ago by Kogan and Susskind, at least one form of this Hamiltonian, on a special lattice. So what are these gauge theories? I don't want to say much about them except for just a few specific properties. So the Hamiltonian is a collection of 4 types of terms. One is associated with the hopping of the fermions on the lattice in a gauge invariant way. These fermions could be quarks, could be leptons in the standard model. But then you also have the mass of the fermions. Both leptons and quarks have mass. But importantly, there is an energy that is stored in electric field and energy that is stored in the magnetic field. Now, if you have just electromagnetism, these are the usual electric and magnetic field interactions or Hamiltonians that you're familiar with. If you have these non-abelian gauge theories in the standard model, then you have a non-abelian form of those electric and magnetic fields. A bit more complicated, but in the end of the day, similar in nature. So now, this is a very simple or simplified picture. Let me tell you a few properties of these Hamiltonians. Well, the first thing is that this is an infinite dimensional Hilbert space because we have bosons. And we have bosons everywhere, right? Because it's a quantum field and it permeates everywhere in a space. And so we have these bosons everywhere in a space, and we have to kind of find a way to truncate their Hilbert space to fit them in our computers, right? So it turned out that there are 2 types of bosonic variables in these theories. One is an electric field, and the conjugate variable to that electric field is something that we call a gauge link. So these are conjugate variable pairs. It turned out that for these continuous gauge groups of the standard model, the spectrum of the electric field is discrete, but it's unbounded. And the spectrum of the gauge link is bounded, but it's continuous. So no matter what, we have to deal with infinite degrees of freedom because these are continuous groups. But depending on which of these conjugate variable pairs we pick to become the bases in which those operators are diagonal in, then we have to come up with different truncation or digitization strategies, understand the truncation error as we take the continuum limit. So that's part of the theory, understanding, and developments that are going on at the moment. Another property of this Hamiltonian is the fact that for these gauge theory systems, there are a number of Gauss's law operators that commute with this Hamiltonian. And only a particular eigenvalue of these Gauss's law operator is what defines the physical Hilbert space. And those are the states that are annihilated by this Gauss's law operator. Okay? So this is very similar to what you have seen in electromagnetism. The charge has to be balanced by the flux of the electric field that comes out of the surface that encloses that charge. Now you can generalize this idea to non-abelian theories as well and on a special lattice. Okay, so these are the set of Gauss's laws. So in other words, we're dealing with a very big Hilbert space, but only very small portion of it is physical. If we try to limit our simulations to the physical sector, kind of encode everything only in terms of physical degrees of freedom, then we lose sort of that simplicity of the Hamiltonian. We are dealing with a much more complex and long-range Hamiltonian compared to the one that has some sort of redundancies built in such that we have a local formulation of these gauge theories. So we have to think about those trade-offs as we come up with Hamiltonian formulations for these gauge theories, given these constraints. And of course, as with other Hamiltonians in other disciplines, we have to think very carefully about the bases and representation. And depending on which basis and representation that we pick, some of these Hamiltonian terms might become simpler or more difficult. And we may end up with Hamiltonians that are sparse or block diagonal or near diagonal and so on. So this is an art to find the best basis for these complicated gauge theory Hamiltonians. And because of all those considerations, there is a lot going on to understand what are the best representations and formulations of these Hamiltonian gauge theories for quantum simulation. This is probably not an exhaustive list, but I try to think about a lot of things that are coming out in the past few years, new ideas and so on. And indeed, we don't yet know which one to pick. In particular, as we take the continuum limit, but we are starting to kind of learn bits of pieces to be able to put the puzzle together, understand which one of these formulations might give us better computational complexity as we take the continuum limit. And I have given also some examples in the realm of simpler theories, like a scalar field theory that some of you might be more interested or familiar with. Okay, so this is really a hot topic on the theoretical front. So let me tell you a bit about algorithmic development. So again, this is another forefront, vibrant research area. The algorithms for simulating quantum field theories really started from the pioneering work of Jordan Lee Preskill in 2012, when they showed how to simulate the scattering of particles in quantum field theory using quantum computers. Okay? Even earlier, there was a paper on Burns and Yamamoto in 2006 when they talk about quantum computing SU and gauge theories of the standard model. So I would say maybe that one is even more pioneering. But since then, there have been a lot of developments on algorithmic side for understanding quantum computational costs of simulating a standard model gauge theories, U1, SU2, and SU3, with some caveats. But there's a lot of work that is still needs to be done on that front. So let me make it simple and just tell you about a few numbers that came out of some of these papers that would tell you an idea of the quantum computational cost of these problems, so that maybe you can then go and compare with your favorite model in your own discipline to see where we stand. So let's talk about this problem of starting from the standard model interactions. In this case, the strong force is the more complicated part of the standard model to simulate. It's an SU3 gauge theory with all sorts of quarks in 3 dimensions and so on. So really, that's the dominant cost of simulating the standard model at the moment. So let's just focus on that and think about time evolution under this strong Hamiltonian, a strong interaction Hamiltonian, in a small lattice, 10 by 10 by 10. And let's look at the electric field bases and set a cutoff of 10 on the electric field values, whatever that means, in this SU3 field theory, it doesn't matter. Some lattice spacing that is pretty small, some fixed parameters with an error of 10 to the minus 3 for the time norm of the time evolution operator error. And it turned out that already this problem requires 10 to the 10 qubits. Okay? So this is not a near-term problem. We need our larger scale fault-tolerant quantum supercomputers to be able to do this. So let's just get that out of the way. Now, what about the gate complexity? So there was this very nice paper by Kan and Nam in 2021 when they looked at second-order product formula for this problem and used non-local Jordan-Wigner transformation for fermions in 3 dimensions. And they came up with this huge number, 10 to the 53 gates. Okay, that's pretty depressing, right? So if that would have been the end of the story, it would have been bad. But it turned out that you can already take that algorithm and reduce that cost by 14 orders of magnitude if you just do better term decomposition in your product formula. Okay, so that's something that we showed with my former postdoc, Jesse Stryker. But can you do even better? It turned out that yes. There was this nice paper that came out last year by Rode et al. I think Mason is in the audience, when they apply near optimal time evolution algorithms as opposed to product formulas. And they also implement local fermionic encoding in these 3D problems. And they come up with a number that is already 25 orders of magnitude better than Canon now, right? So that tells you that at that time, when we have such a large problem, we're thinking about fault tolerance, we are in that asymptotic regime where we have to really switch over maybe to more near or optimal algorithms. The question is whether we can still improve upon those product formulas, because there are a bunch of things that are loosely bounded, and we may be able to, in practice, do even better. The question is, what is next? Where do we want to be comparable with other fields, right? Because if you think about some of the biggest quantum chemistry problems, they're still better than this number. So we really want to push algorithmic developments for this problem. Well, you may ask, how do we do at the moment with classical supercomputers? Because I can actually calculate QCD properties or strong force properties, these nucleons, from first principles on a classical supercomputer. We cannot do dynamics of this sort, but we can do static properties and so on. So let's compare some numbers. Classically, nowadays, we have access to fractions of these exascale machines, for example, at Oak Ridge for each of these calculations. And these exascale machines have 10 to the 18 floating point operations per second. That's their capability, okay? So we're talking about maybe multiplying this number by a factor of 1 million, right? And you can see that you already get comparable to these gate costs. So this should not be too surprising to see numbers like this. And we have access to 10 to the 15 bytes of memory, petabytes, okay? So these are huge computations. We shouldn't expect to be able to run these on the machines today, because even classically, they require a lot of resources, but we can do them now. We could not do them 40 years ago. That's the perspective that we should have, and we shouldn't be discouraged by numbers like this. Eventually, we need these super quantum computers to be able to run these computations, okay? So now you may ask, what about that other path that I mentioned in the beginning? Because I said you can also have an effective sort of approach when you start from nuclear Hamiltonians, these Hamiltonians between protons and neutron degrees of freedom. Would that help to reduce this cost? It turned out that it does, as is expected. Let's think about time evolving something like a calcium, which has 14 protons and neutrons in them, calcium-40. And we evolve it under certain effective field theories, which is the simplest one that you can think about in a 10 by 10 by 10 lattice. Fixed parameters. Now the error is set smaller, which is enough for these kind of problems. Already you see that you need 10 to the 4 qubits. So this is not too far in the future, hopefully. Okay? So this is maybe doable. So again, in this pioneering work by Zohreh et al., they applied second-order product formula to this problem, non-local fermion encoding. They see a CNOT depth of 10 to the 11. Okay? So that's sort of the complexity of the circuit is of that order. Now, we applied, again, the second-order product formula, but we tried to bound the error better based on the fact that you have these fermion number symmetry in the problem that you can take advantage of. And you can already see that you can get 5 order of magnitude improvements by doing so. We also use a local fermionic encoding for these 3D problems. The question is, can we do better still? And perhaps yes, the answer is yes. In fact, as of 2 days ago, there was a few days ago, there was this nice paper again by Zohreh et al. When they applied the first quantization. I think there is an error. No, I think that's good. First quantization, and also these quantum signal processing-based methods instead of product formulas to the same problem. In terms of number of qubits, you need hundreds. So that's much better in this approach. And in terms of the gate complexity for this problem, they get something comparable, maybe 1 order of magnitude better. But you're going to see much more improvement as you go to larger system sizes that I don't have here. So make sure to check out the paper. So again, this is a very evolving field. And we're still coming up with better and better algorithms and better analyses to be able to push these numbers farther down. And let me just skip this. How much time do I have?
You should be wrapping up.
In how? Now? Oh, okay, all right. So can I take 2 minutes? Just like, okay, good. So I didn't get to talk much about a lot of the stuff that has been going on the hardware for these problems, even today. Of course, these are going to be really simple problems because, as I said, the hardware does not fit our overall goal, which is like really a standard model models without any approximation. And I have given you a bunch of slides here that you can check out later on the kind of questions that we can already start to explore today in terms of evolution of matter, pair production, some of the early results and some of the later results on both abelian and non-abelian gauge theories of relevance to the standard model. Some really interesting work on thermalization. I'm not going to talk about this much because the next talk by Nicholas is going to cover that front. Some really interesting work as of last year on dynamics of a string breaking, which is a very nice phenomena in QCD. When you pull apart two charges and you create more and more charges out of the vacuum because of the confinement. So there have been a bunch of analog and digital quantum simulations on different hardware as of last year. They started to look at dynamics of this process. You can create vacuum and hadronic states on a quantum computer. Some of the interesting results are, for example, this 100-qubit Schwinger model vacuum and hadron propagation on an IBM. So these are really sort of the state of the art using the recent technologies on the hardware side. Some really interesting results as of a few months ago on hadron scattering engaged theories on the hardware. And I want to show this slide because I talked about both beta decay and double beta decay in the beginning. These are some of the early results in one-dimensional QCD problems when you can look at the same problems in real time using the quantum hardware. So make sure to check out the slides for this. And some results that were already mentioned on phase diagram. And then finally, on the co-development side, there are a bunch of work that are ongoing, very, very active frontier, trying to understand how to leverage multidimensional and multimode interactions in various different platforms for gauge theory interactions. Again, we saw a very nice talk by Ken on that front, so I don't have to say much about that. And really, sort of as a final word, there's a lot going on in trying to leverage quantum computing and technologies to connect the standard model to phases and dynamics of matter. And we've made a lot of progress. We still need to make more progress to be able to push these algorithmic costs down. But I think the message is that we are, compared to a few years ago, we feel like we've made quite a bit of progress on that front. And with that, thank you very much.
Great. Thank you very much for an awesome talk, Zohreh. We've got time for maybe one quick question. Anyone in the audience? Yes.
So thanks a lot for the very nice talk. You mentioned that for lattice QCD to really develop to what it is today, this co-design with hardware producers was also important. Do you think that, how do you envision the first really useful quantum computer for these problems to be? Like, for example, would it be a purely, let's say, qubit system, or would it be like a platform where you have some fermionic degrees of freedom and some like qubits to encode your gauge?
That's a very good question. And I think in terms of the cost, a lot of cost really comes from these gauge boson interactions and the fact that they have big Hilbert spaces. As I said, in order to take the continuum limit, it turned out that we need really high cutoffs. No matter what representation or formulation you look at, you always have to worry about fitting more and more bosons to take that limit. And if you kind of go through some of these algorithmic analysis, you realize that these bosons are very costly part of the operations, whether it comes to implementing the Hamiltonian terms or exponentiated Hamiltonian terms and the encoding into the qubits. So I think, yes, ideally, we would like to use bosons to encode bosons and fermions to encode fermions. And we are hoping that those kind of platforms would become available for these systems so we don't have to really convert thanks to this like T-gate cost in terms of the qubits encodings. So that's really our hope. Whether or not the hardware technology would get to the point that we have fault-tolerant, larger-scale bosonic fermionic systems to do these problems, that's a different question. But that's really our hope.
Okay. Let's thank Zohreh one last time.